In this video, we will introduce the second half of the second chapter, which is on transformations. So we're going to introduce quite a few functions today because in this unit, we will be transforming quite a few different types of functions. So just to quickly refresh your memory, we did talk about transformations in grade 10, okay? So you transformed the parabola. So the equation of the original parabola is f of x equals x squared. And you created all these different types of parabolas from your original parabola of f of x equals x squared. Now, if you think back to last year, you could have chosen any parabola to be the original parabola. But because of the simple nature of f of x equals x squared, you can argue that it's the simplest quadratic function you can possibly work with, and that makes it a pretty good idea to choose that as the original. But instead of saying the original, we're going to say the parent function, okay? So what we're going to do today in this lesson is study the parent functions before we introduce the ideas of transformation. Which makes sense. We want to have a very good handle, a very good visual of the parent functions before we start manipulating them. So if I were to make an argument why that's a good idea, try to transform a parabola, or try to ask your little brother or sister if they were in grade 3, hey, how would a transformed parabola look like? Well, it's not that they find the idea of transformations challenging, it's that they don't know what the original parabola looks like, okay? So it's very important you know how the parent function looks like, how the original function looks like before the transformations, because otherwise it'd be very challenging to know how the transform function looks like. So what are we going to transform? What are the parent functions we're working with? So let's take a look here. All right, so we have f of x equals x. So that, you know what, that's our classic grade 9, our linear function. Okay, and let's sketch that. Oh, we can sketch that. So y-intercept of 0 and slope of 1. Beautiful. Okay. Domain, all real numbers. Range, all real numbers. So we're probably not going to transform the linear function because it's not that exciting. It's really not that exciting. Quadratic function, we should be really good at this one. So next parent function is the quadratic function. So this one you should be very good at because you've transformed it many, many times last year. So just a general sketch. You could find the exact points, but we are just trying to give ourselves a quick little visual of how the parent function looks. Because when I sketch transform functions, I do them very quickly in my mind. And it's, I can only do that because I know how the parent function looks. Oh, that was not very pretty. Let's save that. Oh, that's good enough. Okay, so the domain here, all real numbers, and the range is any value greater than or equal to 0. All right, okay. What about the next one? Okay, so now we're starting to introduce things that we haven't seen before. So you should, you know, that linear function, that's very straightforward. Quadratic function, very familiar. Now this one, root x, that's the square root function. Okay, how does this graph look like? Well, you know what, you can try to imagine how this graph looks like. That's how it looks like. Now, why is it, let's state the domain and explain why that's the case, okay? So if you look at the domain, x has to be greater than or equal to 0. Any real number greater than or equal to 0. Does it make sense that it's greater than or equal to 0? Of course, because it's the square root function. You're square rooting x. The output is obtained by square rooting x. Well, I can't square root a negative number if I want the output to be a real number. Okay? If I want to get a real number, I can't square root a negative value. So it makes sense that the domain is x is any value greater than or equal to 0. So it makes sense you'll get this graph. And the output values, because you're square rooting 0 or positive values, the output are going to be 0 or any positive number. Okay, so the range is going to be any value greater than or equal to 0. So based on the restrictions on the input and output, or x and y, you have this beautiful graph. And the way it increases, it tapers off. It looks like it's tapering off. Now, it's going to go up forever, but it's just going up slower and slower because you're square rooting, right? Later on the next sheet, you'll see the points, and it'll make sense why it looks like it's tapering off. Okay. All right. What is 1 over x? 1 over, that's called the reciprocal function. Okay. The reciprocal function. How does the graph of the reciprocal function look like? We've seen it earlier in the year. Okay, this is the reciprocal function. The reciprocal function has what's called asymptotes. Okay, so there's a vertical asymptote and a horizontal asymptote. So the horizontal asymptote is located on the x-axis, which has an equation of y equals 0. And the vertical asymptote is located on the y-axis, which has an equation of x equals 0. So how come we get this graph when we work with 1 over x? Well, think about it. Okay, let's explain the horizontal asymptote. So if you study the equation, if your input values, okay, let's say they're positive. Let's say they're positive. If the input becomes greater and greater and greater in magnitude, can you imagine that the output values will get closer and closer to 0, right? Look, if it was 100, you have 1 over 100. Okay, that's 100th. If it's x is 1,000, that's 1,000th. So you're gonna get closer and closer to 0, but never reaching 0. Another way of seeing it is if I have a cookie, I share it between 10 people, and then I share it between 100 people, and then a billion people, I'll get like a very, very, very tiny piece of the cookie. But you know what? That's the bad news. The good news is I'm always going to get some cookie. I'm always going to get of some sort. So that's why it makes sense that you're approaching 0, but never reaching 0. And you can apply the same idea if you sub in a large negative value. If your input is a large negative number, it's the same idea. Okay, you're going to approach 0, but never reaching 0. Now, what about the vertical asymptote? Can we explain the asymptote? When x is approaching 0, when the input value is approaching 0, you'll see that 1 over, let's see, 1 over 0.1, 0.1 is 10. And then 1 divided by 0.01 is 100. So if you get closer and closer and closer to 0, whoa, the numbers get bigger and bigger and bigger, right? And of course, they could grow greater in magnitude with a positive value or a negative number. So yeah, that explains why you have vertical asymptote and a horizontal asymptote for the reciprocal function. So if you ever forget why that's the case, just study the equation. Just look at the equation, and it makes perfect sense. All right, so domain and range. For domain and range of the reciprocal function, we have restrictions on domain. So x can't be 0, any real number, but not 0. Okay, because if it was 0, you have 1 over 0, which is undefined. And what about the range? Well, the restriction on y is that y can't be 0 as well. You can achieve any value by letting x be a real number except for 0. 1 divided by something is never going to give you 0. Okay, last function. So this is a bonus. Okay, this is a bonus one, the absolute value function. If I can spell it, absolute value function. All right, so what does the absolute value function look like? It looks like a V. It looks like a V. Why does it make sense to look like a V? Oh, and by the way, it's also symmetrical about the y-axis. Okay, I don't know if you can tell from my diagram or from my graph, but it is most certainly symmetrical with respect to the y-axis. So it's not that makes sense because we're taking the magnitude of the input. Okay, that means we ignore the sign. If you subbed in 1, you'll get an output of 1. If you let x equals -1, what's the magnitude of -1? What's the size of that number? That means you ignore the sign. The magnitude of -1 is 1. So that's why it makes sense. So, I didn't want to introduce the numbers, but I will here. Right? It makes sense to have that symmetry with respect to the y-axis. And it makes sense to have a V shape, okay? Because we're taking the magnitude of the input. So if that's the case, if we're taking the magnitude of the input, that means x will be greater than or equal to 0. Oops, I meant that for the range. X is any real number. But for your range, the output values will be greater than or equal to 0, okay? Because you're taking the magnitude of the input. Okay, so you can let x be any real number, but the output values, the y values, will be greater than or equal to 0. So that's it. That will be all the functions which we're transforming in this unit. So let's go over them. Linear function, quadratic function, square root function, reciprocal function, and absolute value function. Okay, so your homework is to really be able to sketch the parent functions like in a nanosecond. You need to know how the parent function looks like because it will be very, very difficult to know how the transform function is going to look like. It'll be very hard to tell if you're correct or not because you don't know the parent function. Okay, so to help you with the parent function, I'm going to give you the points. Okay, so these should help you better understand the functions themselves. Okay, so being able to graph the parent function consistently is very important when it comes to transformations. Creating a general sketch is nice. That's what we did on the first page. But if you wanted some accuracy with your graph, we're going to need some points. Okay, so having a table of values. Okay, that will allow us to generate a beautiful graph on grid paper every single time. Okay, so for linear function, quadratic function, I did that for you because it's nothing exciting. You did this in grade 9 and you did this in grade 10. So if you look at the quadratic function, you want 2 points to the left of the vertex and 2 points to the right of the vertex, and that will give you that beautiful, I don't want to say U shape, but yeah, it's a beautiful parabola. Okay, so you don't want to pick points like 0, 1, 2, 3, 4, 5 or 0, 1, 2, 3, 4. Because if you pick 0, 1, 2, 3, 4, what's going to happen? You're going to get the right half of the parabola, right? So it makes sense that we pick these x values, okay? Try to make sense like of why we're picking these values. These aren't just some random numbers we picked out of thin air. Based on the understanding of the quadratic function and its graph, it makes sense to choose these values. Okay, so same idea. We really want to understand the square root function. So these are the points 0, 0, 1, 1. And you might be thinking, should I put 2? Well, let's see. If you put 2, what's f of x? It's root 2. Well, that's silly. Can you plot root 2? I can't plot root 2. What is root 2? Here, let me help you. Root 2. Yeah, can you plot 1.4142135 and it goes on forever? I can't plot that. So why are we using that point? That's a silly point. So if you let x equal 3, you'll have root 3. That's silly. I can't plot root 3. Okay, but you know what I can plot? The 0.42. You know what else I can plot? 9.3, right? So these points aren't just some random points on the square root function. These are points I can actually plot that I can work with and transform. Okay, so yeah, and guess what? These are perfect squares. Your inputs are all perfect squares. That's how you get a nice clean output, because this is a square root function. Anyways, try to make sense of it. I'm going to skip the reciprocal function and come back to it. So for the absolute value function, I know I'm going to get a V shape. I want the tip of the V, of course. And then I want 2 points left and 2 points to right, so I get both sides of the V, just like with the parabola. Okay, and of course, take the magnitude of the values. Bam, there we go. So don't memorize these points. I don't want you, it's too much to memorize. You're going to forget something. So really try to understand how we're getting these points. All right, one more reciprocal function. Why did I skip this one? Because this one, we don't agree on the points. Like this one's a little funny. Okay, so I'll show you why that's the case. So, okay, so now let's find the key points for the reciprocal function. So we have -1, 1, and 1, 1. Oops, -1, -1. And that makes sense because the reciprocal of -1 is -1, and the reciprocal of +1 is +1. And these 2 points are really nice. They're very nice to plot. And these are the only 2 points on the reciprocal function which have coordinates that are integers. Okay. The next 2 points I'm going to write down. The coordinates won't, well, both coordinates won't be integers. One of them might be, but the other one won't. So there are different choices here, but I'm going to choose -2, -1/2, and 2, 1/2. Okay, so if you can imagine your reciprocal function, you'll have 2 branches. So this is very nice because you get two points on each branch. So one more time I'm going to say this. Please do not try to memorize the points. Try to understand where the points are coming from, and that's based on your understanding of the function that you're working with, whether it's linear function, quadratic function, square root function, reciprocal function, or absolute value function. Okay, so hopefully you're now ready to transform it.